Right, good evening, everyone. So I believe last week I kind of left you guys hanging with the what was it? The derivation for the two-port network. So I'm just going to quickly just jump back and quickly recap on this, and just quickly go through the examples that are in the slide. So you guys also note that the examples that I have in the slides are all for the exact method or the precision method. But again, just to quickly recap on what everything means. So essentially, if we take a look at the input side of maybe let me just go through the steps that we need to take here as well. So first off, you take your amplifier circuit, you identify all the voltage sources, then you short circuit all the voltage sources, and then you find your equivalent two-port network with your H parameters for your transistor. All right, so that's pretty much what we're going to get here for a common emitter circuit. So you're basically going to have your source, your voltage source, applied to your amplifier. That's going to be short circuited. And any capacitance is then also going to be considered a voltage source and will then also be short circuited. Right. So as you guys can see, essentially, your base resistance is then going to be connected between your base and emitter. Your collector resistance between your collector and emitter. And yeah, so because of the emitter capacitance here, you're basically just going to short out your emitter resistance here. So that's not even going to feature in your equivalent circuit. And then you're going to end up with Z1, or you're going to end up with a circuit that will look something like this. And usually the H parameter, yeah, I say usually, but the H parameters will be given to you guys. So you don't have to worry about calculating those values. That will be given to you. So you're going to have your input side of your amplifier and your output side. And yeah, so basically your Z1, that's going to be the input impedance to your transistor, looking from your base, yeah, so looking from between your base and emitter towards the output of your amplifier. And then Zin is the total input impedance of your amplifier. So basically looking in on the input terminals from your amplifier towards the output terminals. So essentially, just getting back to Z1, essentially what you're doing is you're reducing the whole right-hand side of your amplifier there after the base resistance into one impedance. And you can do, yeah, so basically we do that on the output side as well. So for the output side, we have Z2 and Z out, where Z out is the output impedance of your amplifier, and Z2 is the output impedance of your transistor looking towards the input. Right, so that's pretty much what that's gonna give you. We also looked at the formulas as well. I'll go back to those in a moment. And also what's important to keep in mind is that the load impedance, so ZL, that you will acquire looking at the impedance on the output terminals of your amplifier, actually on the output terminals of your transistor, not your amplifier, looking towards the output. Right, so ZL, if you don't have a load resistance, your load impedance is just going to be your collector resistance. And if you do have a load resistance, that's then going to be the parallel combination of your load resistance and collector resistance. Okay, so just to recap on that, I'm just going to quickly jump here to the formula. So there's the approximate method formulas. I'm not going to spend too much time on the approximate method formulas. As you guys can see, they're quite easy. They're not too difficult to remember. And then there's also the exact method. So these ones are a bit more tricky. I see I haven't. Let me maybe just make everything available for download as well. Okay. Okay, so yeah, so let's maybe take a look at a bit of an example. So we actually have one here explaining the whole process. So as you guys can see, we are given some of our parameters there on the right. First being, we have the base resistance as 200 kilo ohms. We have the collector resistance as 1 kilo ohms. And we have our input, the input impedance of our transistor as 1.5 kilo ohms. The reverse voltage gain is 2 times 10 to the power of, let me just see if I can hide this thing here. Okay, for some reason I'm struggling to reduce this toolbar here. But in any case, not too sure what that value is. We can probably see it over here. Yes, we do. So 2 times 10 to the minus 4. The forward current gain is 60, and our output conductance of our transistor is 25 microamps per volt. Okay, so we can go and calculate our current gain. So if we use the exact method, so in this case, we are ignoring current division. So if we were to include current division, we will have to multiply so then the formula for that current division is going to change to, I'm just trying to remember here what that I included here in the formulas. I don't think I did. Let me just get this from an old question paper real quick. Okay. So that's going to be your total base resistance. Now the reason for the total base resistance is sometimes you will have something like a voltage divider bias amplifier, whereby you'll have 2 base resistors, and then you're going to have an equivalent parallel base resistance circuit there. And yeah, so the current is then going to split between RB and Z1 there. And the other factor that you can multiply with, and this one will only be applicable if you have a load resistance. So if the load resistance is 0, then obviously RC over RC, that's 1, and then multiplied by HF over 1 plus HOZL. Okay, so there's the formula, including current division as well. So yeah, so in an exam, if current division isn't asked, you don't have to do it. But if it is asked, sometimes they will ask it in a way that it sounds like you don't have to do it, but rather do it than not, because the subject's exams can be quite finicky and honestly a little bit funky. Questions can sometimes be quite weird for industrials in 5. I don't know why, but anyways. Okay, so for this particular example, we're going to get 58.537 as our current gain. Now, if we did consider current division, so pretty much we're just going to have current division here at the input side. Yeah, that's basically then going to result in a somewhat lower current division, current gain, right? So, but yeah, so that can, so depending on how well your amplifier is designed, that can actually be either a very big difference or a very negligible difference as well. And then calculating the voltage gain, again, there's the formula. That's pretty much what we're going to use. And yeah, so for common emitter amplifier, that's usually going to be a negative value. So that's going to be minus 39.331 for this particular example. And also take note that ZL in this case is equal to the collector resistance. And then we have, so you guys will see, I have a few worked out examples for you guys in the slides. Just feel like we might have to maybe do one of these as well. Let me see, what did we do last week? Okay, last week we did do an example, so. But anyways, as you guys can see, there's a lot of rinse and repeat stuff to do. The current division rule that I have here in the examples, I have a bit of an old way of doing it, or rather, there is another way of doing the current division, which I don't really like that much. It's a bit complicated, but it essentially boils down to using this formula, except you basically go and calculate the fractions for each of these resistor combinations. Go and calculate that separately and then multiply it with the current gain. But that's a bit of a clunky way of doing it. So you guys will see, so you basically take it, okay, cool, how are you going to calculate what I1's value is going to be? So you're going to get a fraction multiplied with the input current, and that fraction is then what you use to multiply with the current gain to get the correct current to correct for current division. I just want to see, okay, so here's an example, and I just want to make sure about the values here, if it's the same as the previous example. No, it actually isn't. Let's see, an example more back. Actually, no, the same example on its own, but in any case, so you guys can see when you add the load resistance, your load impedance is going to change. So for this particular example, instead of using 10 kilo ohms as our load impedance, we're now going to use 1.66, well, you can say 1.667 kilo ohms. And yeah, that, as you guys can see, that can actually drastically change what Z values such as Z1 is going to be, because we do have ZL there. And it can also influence your output impedance quite a bit as well. It's also going to then influence your current division as well, because now you also have current division on the output. The way the current division is done in this example is not right. You have to use this formula, that formula that I showed here in the beginning. So this one here. Right, but yeah, but you guys can go work through these examples. Yeah, so I'm going to wrap up with chapter 1, and then we can start with chapter 2. We are a bit behind. So again, I just want to go through the types of distortion here. So you can have quite a few factors that will influence distortion. So this is something that you're going to encounter with any amplifier. So you're going to get things like nonlinearity of your input characteristics. So that's also going to cause distortion. So basically, the how can I say, the relationship between current and voltage is not necessarily linear for the input of an amplifier. Then you also have your Q point or operating point of your amplifier is not correct. So this is particularly true for transistor amplifiers. So if you don't pick your operating point correctly, you can run the amplifier into saturation prematurely, which is then going to cause your output to be distorted. You can also have a situation where your input signal could also be too large, driving your amplifier into saturation and thus distorting the output waveform. And you can also have mismatch of impedances between your load and amplifier. So for instance, if you have, or just between amplification stages. So if, let's say, the output of your amplifier here, so Z out here is high, but your load impedance is really low, that's going to cause unnecessary loading of your amplifier, and that is going to distort your output waveform. So essentially what you want to do is you want your output impedance of your amplifier matched to your load impedance, right? So essentially you either want a high output impedance matched with a high load impedance. So you want these two values to be, how can I put this? You want them as close as equal to one another as you can get. And then also, if your load impedance is low, you also want a low output impedance from your amplifier. So that would be then a matched, yeah, so that would be matched impedances. Now, we're also going to take a look at three different types of distortion here: amplitude distortion, nonlinear distortion, and frequency distortion. So amplitude distortion, this is usually caused by the Q factor, or the Q point rather, or your operating point of your transistor incorrectly selected. So meaning essentially what's happening here is your biasing point of your transistor is to a higher voltage. So essentially you are driving your amplifier into saturation. So yeah, so and another thing, yeah, so you can only amplify up to the supply voltage, right? So if you are working to, if your Q point of your transistor is too close to, let's say you're supplying your amplifier with 15 volts, then you are operating way too close to your supply. So you're going to drive your amplifier into saturation. And actually the same thing can happen if you pick your Q point too low as well. So if your Q point is too low, you get into a situation, so that would be 0 volts or minus VEE. Actually doesn't matter which. Let's say it's 0 volts. So here your Q point is too low. Right, so again, you're driving your amplifier into saturation there for that negative half cycle. And then if the magnitude of your input signal is too big, you're going to drive your amplifier into saturation on both your, how can I say, your negative part of your waveform and the positive part. So yeah, so another name for this phenomenon is what we call chopping. So you're basically chopping the top part of your waveform, or the extremes of your waveform. You're basically chopping off in a sense. Nonlinear distortion, again, this is typically caused by the nonlinearity between your input characteristics. So essentially, the voltage on your voltage and current is not necessarily going to have a linear relationship for your transistor. Particularly if you look at the base emitter voltage and the base current. So if you operate, so ideally, if you look at this curve, you would like your input to operate, yeah, so you would want your input within that range there for your base emitter voltage, because that means you're going to have more or less a linear relationship with the current. But further out, like we have here in the example, you are operating over a nonlinear region of the curve. So that's going to give you a distorted output, right? So yeah, so because BJTs, or bipolar junction transistors, are basically current-based components. So if your base current gets distorted, that's also going to distort the voltage across your collector and emitter as well. Now, we can negate this type of distortion at the input of your amplifier. And usually this is done with a high output impedance current signal source. So yeah, which will allow for a non-distorted input to your amplifier. Okay, so also, yeah, again, you can also bring maybe the base voltage down a bit. Yeah, like I said, you want to operate within a linear region of this curve. And then frequency distortion. Yeah, so frequency distortion will mainly be caused by reactive components, so things like inductors and capacitors. So essentially, this is just due to the fact that the response, or rather the impedance of these components, are dependent on frequency. So that's then also going to influence your output that you get from your amplifier. So that will also mean that your amplifier has a certain bandwidth that it will give you a stable output. So as an example, if we have an amplifier with a frequency response that looks something like this, almost like a bandpass filter almost, there will be a range of frequencies that will give you a pretty stable output. Now, where the output is at RMS value, or actually the better definition here is that where your output is at half power, that would be at what we call the -3 dB point. So it's where basically these points here, and that will be also your cutoff frequencies, and that will then describe your bandwidth. So yeah, so at low frequencies, the gain of your amplifier will be very low, and that's mainly caused by any coupling capacitors that you have. So if I can quickly go back to one of our circuits here, so that there, it's a coupling capacitor. So at low frequencies, so depending on the size of that capacitor, that's going to depend that's going to influence the low frequency range of your amplifier. So at which point, so basically at which point that cutoff frequency sits. And you also get the same drop off at the high end of the frequency spectrum, where the reactance of basically the output of your amplifier will pretty much approach zero with the increase in frequency. Right. Okay. I think, then that's it for chapter 1. So I'm going to go on to chapter 2 here. I see we already kind of lost half an hour here.